Very good morning. In the last lecture, we have revised the concept for power series. Okay, and we try to identify how do we define the radius of convergence, or in short, interval of convergence. And we have also seen that in the interval of convergence, function has this power series expansion has very nice properties, such as you can differentiate term-wise, you can integrate term-wise, means you can perform the individual, means like each term you can perform the derivative and then you can sum up again. And you can also perform the integral of individual term, okay, and then you take the sum of it. And that is only possible inside the interval of convergence. Outside the interval of convergence, you can't say. So there other important things will take place if you are looking at outside interval of convergence. Means you have at some particular point, and you have to investigate whether the given power series is uniformly convergent or something, okay, which we have not defined yet. Okay, so with keeping that in our mind, okay, so let me give you the definition of definition that a function f when it is said to be analytic at certain point. Okay, so it's means like what do you mean by means like analyticity? Okay, it's going to be more than even differentiability of a function. Okay, in some sense. Okay, so that more this word is borrowed from you can say from the complex analysis. Okay, and it's like if it is a function may be differentiable at a point. So if it is also suppose at x0, and if it is also differentiable in some neighborhood of it, okay, then we say the function is analytic. So it is more than the differentiability in some sense. Okay, right. So here is the definition. So if we say a function f with the property that a power series expansion of the form, so we will be able to write f as in this power series expansion, okay, and which should be valid in some neighborhood of the point x0. So what is that neighborhood that you have to investigate based on the problem? Okay, so that may be, say, like some neighborhood. It's not like for all neighborhood of the point. Okay, so you should be, so it may be as small as possible or it may be as large as possible. So it's completely depends on the definition of the function. Okay, right. So means like is valid in some neighborhood of the point x0 is said to be analytic x0. So in a very rough manner, if you are able to write a function f in a power series, means like a polynomial of infinite degree. Okay, so there is no point of I am here like using some abused notation here, like infinite degree. What is the infinity? It is not defined at all. But what you have, what I mean to say is you have a non-ending series, okay, expansion, where you have the coefficients are constants and means like, and it is in powers of x. Okay, means it's increasing power of x or x minus x0. Okay, so for example, you can take the exponential function e power x, for which you know already one of the Taylor series. Okay, set like 1 plus x squared by 2 factorial plus x cubed by 3 factorial and so on. Okay, so it's a non-ending power series expansion of e power x. So you can certainly tell that from there that e power x, that function is analytic about x equals to 0. So now, but the same function you can also expand about the point x equals to x0 as well. So you can write e power x in powers of x minus x0 as well. So there you have to do some adjustment and you got through with it. So you can write e power x as, you can subtract x0 and add x0, and then you use the property of exponential function. Okay, Right. So what are the example of what are the examples of this analytic functions? All polynomials. Okay, all polynomials, e to the power x, sin x, cos x. You are familiar with them. Okay, they are analytic functions. Okay, because you can so you can ask that how this finite degree polynomial. Suppose I have a quadratic polynomial. Okay, so whether it is a it has a power series expansion. Yes, you have. So you have, this is a naught plus a1 x plus a2 x square, where a naught, a1, a2 are equals to 1, and plus an, or you can say summation n equals to 3 to infinity an x to the power n. You can write an is equals to 0. So I have not mentioned that an should be 0 for all, or it should be non-zero for all, okay, coefficients. Okay, so you can write in this form. So it has a power series expansion. So you are already familiar with e power x, sin x, cos x, this infinite series. Okay, so you can these are the ready example. Okay, now if you have two functions which are analytic at some point, so they are like in the continuity and differentiability, you have seen their sum and difference and product and division will also become analytic at that point. Okay, so only you need to take about the division part. So where in the division means like rational function. So numerator is analytic, denominator is analytic. Okay, and provided g of x naught is should not be, means g should not vanish at that point. Okay, so you can also means like look at the rational function in that way. Okay, so you can look at numerator separately, denominator separately, and you should remove the points where the denominator get vanishes. So because that at that point you can't talk about the analyticity directly. So you have to look at some other other explanations. Okay, right. Now these are the about the function of function. When you say a function is analytic and so on, suppose if you have a readily given the power series. Okay, so you have the power series like a summation an x to the power n equals to 0 to infinity. Okay, so the sum of a power series is analytic. So it means the sum is, we are going to identify by some certain function. So you will see later on that this may or may not equals to f of x, means like you may or may not able to identify what will be the corresponding that sum value. Okay, so we are writing it in abstract sense, that is going to be some function of x. It's certainly going to be some function of x, but what is that function? Identification of that is very tough. Okay, only for like e power x, sin x and cos x you may be familiar about. At the more you have 10x, you have at the most, okay, sine hyperbolic, cos hyperbolic, and so on. Okay, they are the familiar function for which it is easy to recognize what the corresponding power series. But if you have been given with any random, we can say random power series, suppose it is like everything is valid, right? This is convergent in the interval of convergence, so means like mod x less than r. Okay, so whatever I'm talking about here, you can replace it by x minus x naught. Okay, because both the series are equivalent, you can obtain from each from other. Okay, so if you have been given with a power series and you know that this is the radius of convergence is in this minus r to plus r, then it is going to be analytic. Okay, in other words, it has derivatives of all possible orders. And you have also seen what will be the how do you find out f dash of x is n time an x to the power n minus 1. One more time, you can differentiate in the interval of convergence and so on. Okay, and from there you can also recognize what is an. You have seen that is nothing but f nth derivative at 0 by n factorial in this case. When you are talking about the x equals to x naught, you have f nth derivative at x naught by n factorial. Means it's falling into the Taylor's infinite series category. Okay, in roughly. Okay, so in the previous like where we have mentioned here, so if you have the power, this function is analytic. Okay, means it has a power series expansion. So your coefficients of this series an can be identified in terms of derivatives of f. So at x naught, so that is given by this formula that you have already seen in the case of Taylor series expansion. Okay, right. Now what we are going to look at is we are going to see how this going to give us help for writing the solution of differential equations. Okay, so let's start with the first order differential equation. Okay, so let us take this one example, y dash equals to y, which is a very simple equation whose analytical solution you are already aware about, that is nothing but y equals to e to the power x, or you can say constant multiple of that, c times e to the power x. So I have not given any initial condition here. You can mention y at 0 is 1, then c can be identified as equals to 1. So what we are going to do here is, we are going to find out its power series solution if it exists. So that so far we have not confirmed that whether it exists or not. Okay, so what we are going to means we have to start with something. So let us assume that this y equals to this infinite series. We have taken about the point x equals to 0. You can start with x equals to x naught as well. Okay, so because here the calculation will be simple and it will be looks like good, so we have started with x to the power n. Instead you can work with x minus x naught as well. Okay, now let us assume the following power series expansion solves 1 in this radius in interval of convergence mod x less than r. So we have already see, once I mentioned this mod x less than r means this series A has interval of convergence that is minus r to plus r. Okay, and we can now utilize all the possible properties attached with this. Okay, means we can do here term-wise differentiation, term-wise integration, and so on. Now, so we have assumed that, let's say this this is solves 1. So we have to identify what are the possible values of ans. Okay, if we are able to identify some an r does exist there for which this becomes a solution, then we are through. And means we, and at the end we also have to comment on this, what will be the possible radius of convergence. Okay, so we have here we have two things to determine. First is the constants an, and second is the radius of convergence. Okay, so we are going to use this, that y equals to this solves 1 means you have to find out what is y dash from here. So you can, it means you can use the previous procedure. We have already given what is y dash is n time an x to the power n minus 1. Okay, and substitute here and compare the coefficient of x to the power n on both sides. Okay, so this is what you have to do when you have to assume, when you have this assumption. So we wish to determine constants, this a0, a1, a2, and so on, at the radius of convergence r. Okay, and we have from 2 we have, so we have, this is, I have already told you what is y dash is summation n equals to 0 to infinity time an x to the power n minus 1. Obviously when n equals to 0, this is 0. So you have started with a1 plus 2 times a2x plus 3 times and so on. So this is what we got in the derivative. Now y dash equals to y. Okay, so we have to now compare it with y dash equals to y. So y dash from 1 and 3 we have. For y dash equals to y means this is left hand side is y dash and right hand side is y. Now you have to compare on both sides. So constant should be equals to constant. Coefficient of x should be equals to coefficient of x. Coefficient of x square should equals to coefficient of x square, and so on. Okay, so what you observe from here, a1 equals to a0, 2a2 is equals to a1, 3a3 equals to a2, 4a4 equals to a3, and so on. So what it will give you, so a1 equals to a0, that's fine. Now 2a2 equals to a1. What does this imply? The coefficient of x. So a2 equals to a1 by 2. But a1 is a0, so I have represent in a0 by 2. Okay. Similarly, the coefficient of x square now 3a3 equals to a2 implies a3 equals to a2 by 3. This implies a2 is what? A naught by 2 factorial. So a naught by 2 factorial into 3. So that's going to be 3 factorial. A naught by 3 factorial. Similarly, for this case, for a4 equals to a3 implies a4 equals to a naught by 4 factorial, and so on. So by observing this, you will find a pattern that you can write an is equals to a naught by n factorial. Now, what you have to do now is you have to substitute this an value in the series. Okay, what you will get is summation n equals to 0 to infinity an x to the power n is equals to an is a naught by n factorial. So a naught is constant, this fixed constant. Okay, summation n equals to 0 to infinity x to the power n by n factorial. Okay, so now what is what is this series, this coefficient a naught times this is nothing but the exponential function. So right, exponential series of about the point x equals to 0. So you can use the ratio test to determine that r equals to infinity. Okay, that radius of convergence infinity means this power series converges for every values of x. Okay, that we have already done during the Taylor series session. Okay, so this is very easy to observe, so you can use the ratio test for that case. Okay, so this converges for every value of x. So you have this radius of convergence that mod x less than infinity, means it converges for every values of x. So such solution is possible, but here again in this case you are easy to recognize what is this series correspond to, and since this once you identify the initial condition that y at 0 is 1, you can identify the unique solution that also relate e power x equals to summation n equals to 0 to infinity x power n by n factorial. Okay, now let's look at some complicated, complicated, or means not, I should not say complicated, but a more general type of series. Okay, and let's see what will happen. So let's say this example. Okay, so y equals to 1 plus x to the power p. So I have started with this function, and I can certainly verify that this is going to solve the following one. Okay, now if you compare this y dash equals to f of xy and y at x naught equals to y naught, you compare with the Picard's theorem. Okay, the function, the right hand side becomes continuous, and you have this all these conditions satisfied. So means Picard's theorem will guarantee that the uniqueness of the solution, means this problem will have unique solution. Okay, so that's here you can say comment here that this problem will have unique solution. Okay, right. So if we are going to determine the series solution for 8, okay, then that series and this solution should be equal. Why? Because of this Picard's theorem guarantee. Okay, that because of the uniqueness of the solution. So that power series should represent this 1 plus x to the power p, and which you already know that 1 plus x to the power p, for p arbitrary constant, you have this binomial series 1 plus px plus p into p minus 1 by 2 factorial x square and so on. Okay, so you will find out. So okay, so let's see. So again we will start in the same fashion as we have done with the first problem. Okay, so let y equals to summation a n x to the power n solves one in this interval of convergence. Okay, so now for substituting in 1, what you require y dash, you require x time y dash, and you require p time y. Okay, so this can be identified. So from here y dash, you can differentiate term wise. Okay, x time y dash, you just multiply by y dash by x time y dash, and p time y, you can just multiply the y by p. Okay, so as simple as possible. So you have this y dash, just now we have already determined that a1 plus 2a2x plus a3x square plus 4a4x cube and so on. Okay, now substitute these values in the equation 1 and then equate the coefficient of x to the power n on both sides. Okay, and try to get some relation between this constants a and, okay, among each other. Okay, right. So 1 and 2. So this y dash x y dash py, this set of equations, okay, it represents 2, and that 1 is a main equation. So 1 plus x time y dash equals to py, means you are going to sum up y dash and this, and you can equate to p term pi. Okay, so what is there? So a1 is a constant term, so that is separate. So a1 plus 2a2 plus a1, because they are the x coefficient. Then x square coefficient is 3a3 plus 2a2. X cube is 4a4 plus 3a3, and so on. Okay, so that is what is here is appearing: a1 plus 2a2 plus a1x plus 3a3 plus 2a2x square, and so on. Now the right hand side is y times p, so a naught p plus a1 px plus a2 px, every term is multiplied by p. Okay, now compare both sides. So a1 equals to a naught p, that's a constant term. Now coefficient of x 2a2 plus a1 equals to a1 p. Okay, so this implies 2a2 equals to a1 times p minus 1. So because a1 p minus a1 is a1 times p minus 1. Now a2 is equals to, right, a2 equals to p minus 1 times a1 by 2. So what is a1 is a naught p, so you replace it everything. So what you will get from here is a2 equals to p times p minus 1 by 2 times a naught. Okay, now with the x square coefficient, what you have is 3a3 plus 2a2 equals to a2p. Okay, so what it will give you, 3a3 plus 2a2 is equals to a2p. So from here 3a3 equals to a2 times p minus 2. So 2a2 is will send this side. So you have a2 times p minus 2 by 3. That will be a3. Now, but a2 is nothing but p times p minus 1 times a naught by 2 factorial. So 3 into 2 factorial is 3 factorial. And you have p times p minus 1 into p minus 2 times a naught by 3 factorial for a3. And so on. Okay. So by following this, so you can also determine one more step, and you can also show that a4 is equals to p times p minus 1 times p minus 2 times p minus 3 divided by 4 factorial times a naught. Okay, so an will be p times p minus 1 and so on, p minus n plus 1 divided by n factorial times a naught. Okay, and now what you do is you just write down in this y equals to a naught plus a1 is a naught px plus a naught times p, so that is a2. So this is a1, so this is a2. Okay, so this is a3 and this is an. Okay, and which you have already you are using this as a binomial series of 1 plus x to the power p. Okay, for p any arbitrary constant. And since Picard theorem gives the guarantee that the solution is unique, so that will give you guarantee that 1 plus x to the power p is equals to this. Okay, so when you satisfy this initial condition y at 0 equals to 1, that will give you a naught value is 1. Okay, so you have the binomial series of 1 plus x to the power p, which is nothing but 1 plus px plus p times p minus 1. So this can be shown, and further it can be also shown by using again ratio test can be applied to show that this series will converge in this mod x less than. Okay, right. Now what we have understood through first order differential equation, like power series solution of first order differential equation, similar things we can apply to the second order differential equation as well, but with some cautions here. Okay, so what are the points which we have to remember for before applying the power series solution to the second order differential equation is, so you have to determine what is the nature of the point x naught. Okay, to certain functions. Okay, so that you will just now see. Okay, so right, so you consider the following homogeneous linear differential equation of second order. So y double dash plus p of x times y dash plus q of x times y equals to 0. Let us call this as equation number 1. Okay, now what is the central fact of means like what is the relation between the solution of this equation and the coefficients? Okay, so that is can be identified by the following fact, that the behavior of its solution near a point x naught means you are looking a solution near some point x naught. Okay, so you can certainly decide, at least you can decide what will be the possible nature of the solution near that point, okay, by using this fact. So it gives you the intuition that the behavior of px and qx, which are known to you, so the coefficients p of x and q of x, you can identify from the equation and see what will be the nature of this p and q near the point x naught. Okay, what is the meaning of nature? Means whether the function this p and q are analytic at x naught or not. Okay, so if they are analytic at x equals to x naught, we say that that point is an ordinary point. Okay, if they are not, means like both I'm talking about. So if both p and q are analytic at x naught, then we say that respective point is ordinary point. Otherwise, we will say that is a singular point. Okay, so we are going to look at, okay, that those cases as well. Okay, so if either one of them is not analytic, okay, then we say that point is singular point. Okay, so for becoming a point x naught to be an analytic point, okay, you need to have, or ordinary point of this equation, you need to have this property that both p and q should be analytic at x equals to x naught. Okay, right. So let's look at some examples. Okay, so this is what I have just now mentioned. A point x naught is said to be an ordinary point of 1 if both px and qx are analytic at x naught. So we say that x naught is a singular point of 1 if it is not an ordinary point. So if it is not an ordinary point, we will say that is a singular point. Okay, right. So let's take one example here. Okay, let us take one example. I want to locate the possible singular point and ordinary point for this equation 1 minus x square time y double dash minus 2xy dash plus, let's say, p time p plus 1 y equals to 0. P is any arbitrary constant. Okay, now if you compare with the original equation, what is p of x is nothing but you have to make the y double dash coefficient 1, means you have to divide by this. So px is standard for minus 2x by 1 minus x square, and what will be the q of x is p time p plus 1 divided by 1 minus x square. Now if you look at these p and q carefully, so let's look at p first. Okay, so you can see the numerator is analytic because it's a polynomial. Denominator is also analytic because this also is a polynomial. Okay, so this rational function is analytic everywhere except at the point where the denominator vanishes. Okay, so p is analytic. Okay, so p is analytic everywhere except at plus minus 1, means where 1 minus x square is equals to 0 means x equals to plus minus. Similarly p, I can say similarly q. Okay, because q numerator is analytic because it's a constant, denominator is a polynomial, it's also analytic, so they are also analytic everywhere except at x equals to plus minus 1. So the function, so x equals to 0 is an ordinary point of this equation. However, x equals to 1 and x equals to minus 1 are becomes the singular point of this equation. Okay, right. So this is an example of how to locate the singular point and ordinary point of the second order differential equation. Yes.
Sir, how we can say that if numerator and denominator are analytic, then the term is also analytic?
So that's what I have mentioned in the starting page itself, that if f is if you recall this here, f and g are analytic at x naught, then f plus minus g, f into g and f by g are also analytic at x naught, provided in the rational function, provided this denominator should not be 0. So like here in the same fashion, it's like what is this alternate meaning is the meaning is you can also represent f by g in powers of x naught simply. Okay, so see, look at here. So I can write this as minus 2x times 1 minus x square to the power minus 1. Okay, and I can write this as p into p plus 1 times 1 minus x square to the power minus 1. Okay, so I can certainly write down in powers of x because I know what is 1 minus x to the power minus 1 is 1 plus x plus 2x, 1 plus x plus 2x square plus 3x cube, right? So, what is
Yes, sir. Yes, got it.
okay. So I think 1 minus x inverse is 1 plus x square plus x cube and so on, right? So you can yes,
certainly we can say that p into p plus 1 would also be an analytical solution.
yes, because it's
okay.
p is fixed. P is any arbitrary constant, but it is fixed. It's a real number when you talk about a particular equation. Okay.
Yes, sir.
It's fine. Yeah. Okay. So this is how you will decide the point, the ordinary point or similar point of the given differential equation. So we are going to focus only for the ordinary point case. For singular point case, we have some different strategy for find out the power series solution. So first we try to identify whether the point is ordinary point or not. If it is ordinary point, then we will look at this power series solution. If it is not, then we have to certainly look after some other special cases where other method will take place, like Frobenius method and so on. So I'm not going with that Frobenius method here. So I'm only restricted with power series solution. Okay, right. So for that, we have this guarantee theorem, you can say. Okay, that theorem will give you the guarantee that it has the power series solution. Okay, so we just now we just now should have this result will give us the confidence. Okay, you can say that confidence or basic theoretical aspect, okay, which is required to say yes, there is a analytic solution at x naught. Okay, so what it says is let x naught be an ordinary point of this second order linear homogeneous differential equation. Okay, then there exists a unique y that is analytic at x naught and is a solution of 1 in a certain neighborhood of x and satisfies the initial conditions y at x naught equals to a naught and y dash x naught equals to a. So you have been initial condition with some y at x naught equals to a naught and y dash x naught equals to a1 that is required for having the uniqueness of the solution. Okay, so this theorem will give you the guarantee that the solution of this power series solution power series solution of this equation 1 does exist. So you have to you have to have information that whether x naught is an ordinary point of this equation or not. Okay, right. So let's look at that case. Okay, so the continuation of this result, what it will give you is that if you are when you are going to verify that P and Q are analytic, okay, at x naught, means you certainly have that Px and Qx will have power series expansion. So means they will be having some interval of convergence. Okay, so that solution will also have the same interval of convergence. Okay, so whatever the P and Q will have this interval of convergence, similarly that Y also will have the interval of convergence. Same interval of convergence will also be there for the solution Y. So this will give you that what I have mentioned is starting that the behavior of the solution Y depends on the behavior of this coefficients Px and Qx. So if you say Px and Qx are analytic in some neighborhood x naught of in some neighborhood of x naught, then that y that solution will also is going to be analytic in the same neighborhood of x. Okay, so this is what the continuation of the result is telling. Okay, right. So let's look at the following this very simple second order differential equation for which you already know the general solution. So I hope you can recall that y equals to c1 cos x plus c2 sin x will be the general solution of this. By using the auxiliary equation, auxiliary roots are plus minus I, m square plus 1 equals to 0. And we can recognize that these are going to be so cos x and sin x going to be the linearly independent solution of this equation. Now what we are going to interested in, we are going to derive the power series solution of this. So we are going to start in the same fashion. So first thing is we are going to look at the power series solution is around x equals to 0. So if you compare with the standard equation, what will be p of x is the coefficient of y dash, so that is 0. What is q of x? That is nothing but coefficient of y, that is 1. They are constants. So constant functions are anyway analytic everywhere. So the solution is also going to be analytic at every point in R. So we certainly can look at the power series solution about any point. So here, without loss of generality, we are going to assume that x naught is 0. So we are going to look at the power series solution near 0. Okay, right. So we have this. So we have started with this assumption that let y equals to this in power series in the interval of convergence mod x less than r. So certainly, see, just now we have told that that by that result that if p and q are analytic at means in some neighborhood of x naught, that is mod x minus x naught less than r, then the y is also analytic in this. So by using that fact, you can certainly say r will be come out as infinity. Okay, so it should be so converges for every value of x. Okay, so that also will be proving it. Okay, here. So like we have proceeded in the first order differential equation, we will proceed in the similar fashion here. So for doing so, you have to get y dash, y double dash. Okay, differentiate it termwise in the interval of convergence and substitute in the differential equation and compare the coefficient on both sides. Okay, so the same strategy we will be adopting here. Okay, so from here you can certainly derive what will be the possible y dash and y double dash. And now from equation, what is the equation is y double dash plus y equals to 0. Okay, so y dash anyway we have already done a1 plus 2a2x plus 3a3x square plus and so on. Y double dash is you have 2a2, 3a3 into 2x. Okay, plus you have 4a3 into 4a4 into x cube was there, so 3 will come and so on. Okay, so what you have in the equation is y double dash plus y equals to 0. So constant, so 2a2 plus a naught will be the constant plus x coefficient is 3 times 2 times a3 plus a1 plus x square coefficient is 4 times 3 times a4 plus a2 plus and so on. Now you compare on the both side, okay, the coefficients of x, okay, and constant term. So 2a2 plus a naught equals to 0, 3 times 2 times a3 plus a1 equals to 0. So all coefficients should equals to 0. Okay, then only this left hand side and right hand side equals. Okay, so that if you do so, so a2 equals to, so first so 2a2 plus a naught equals to 0 will give you a2 equals to minus a naught by 2. So this is what. Second equation, that 3 times 2 times a3 plus a1 equals to 0 means a3 equals to minus a1 by 3 times 2. That is 3 factorial. This is 2 factorial. Now this equation 4 times 3 times a4 plus a2 equals to 0. So a4 equals to minus a2 by 4 into 3. Okay, minus a2 by 4 into 3 plus, so a0 by 2 factorial minus time a0 by 2 factorial is a2. So you replace it. So minus minus plus, you have a0 by 4 into 3 into 2 factorial, that is 4 factorial. Okay, similarly you can show a5 is equals to a1 by 5 factorial and so on. So what you will have, the odd suffixes 3, 5, 7 and so on, you have in terms of a1. The even suffixes you have in terms of a0. Okay, and you have the pattern here. So with a3 you have 3 factorial, with a5 you have a5 factorial, a7 you have 7 factorial, a2n plus 1 will have 2n plus 1 factorial. Similarly for the even suffixes. Now also you can look at that a3 have negative sign, a5 positive, a7 negative, a9 will positive and so on. So alternate plus minus. So that also you can relate carefully. That's going to be minus 1 to the power n when 2n plus 1. So n equals to 1 means a equals to this 2n plus 1 become 3, you have minus 1. Okay, n equals to 2 minus 1 square, so the a5 with positive sign and so on. So this needs to be fit carefully here. Okay, now you are going to substitute these values in the original power series. Okay, so what you will observe, so a0 will be presenting in the, you have the C, a2, a4, a6, a0, a2, a4, a6 will be with even powers. a3, a1, a3, a5, a7 will be the odd powers. So you have this a0 times this alternating plus minus everything here. So also you can recognize that a0 coefficient is nothing but the cosine series and a1 coefficient is nothing but the sine series. Okay, so this will give you the power series solution of the given ODE. Okay, so here it was easy to recognize what it represents. Okay, so let's look at now the case where you may or may not able to recognize the things. Okay, now let's consider this equation 1 minus x square times y double dash minus 2xy dash plus p into p plus 1 y equals to 0. So we have already seen x equals to 0 is an ordinary point. Okay, so comparing with this, we get p of x and q of x are so and so, then which are analytic everywhere except at plus minus 1. So x equals to 0 is an ordinary point. So px and qx are analytic in some neighborhood of x naught. Okay, so there means x naught means that should not be crossing plus minus 1. Okay, neither on one side, neither x equals to 1 nor y x equals to minus 1. Otherwise, it will not become analytic. Okay, right. So similarly, then that theorem guarantees that solution y will also be analytic at near x equals to 0. Okay, right. So by using that fact, okay, so we are going to have this, we are going to consider this power series around x equals to 0. Okay, now you can substitute the values of y dash and y double dash. So what you require here, y double dash you require x square times y double dash, you require 2x times y dash, you require p times p plus 1 times y. Okay, so you have to fit everything here in the one and you have to find out these coefficients. Okay, right. So from here y dash is n times a n x to the power n minus 1. So you can start with n equals to 1 to infinity. Okay, right, because n equals to 0 is 0. Okay, right. What you require is minus 2x times y dash. So I just multiply by minus 2x both sides. So you have this minus 2n times an times x to the power n minus 1 plus x plus 1. That's going to be x to the power n, because one more x you are multiplying. Okay, right. Now you differentiate again here y double dash. So what will be summation n equals to 2 to infinity n times n minus 1 times a n x to the power n minus 2. Okay, so this is going to be y double dash. Now see, I am rewriting this in the form of summation n equals to 0 to infinity. So see here we are starting with n equals to 2 means x to the power 0. n equals to 3 means x to the power 1 and so on. Okay, so when you have n equals to 0 to infinity, you have x power n, that's fine. But what about here, an and this and so on. So when n equals to 2, you have a2, and n equals to 3, you have a3 and so on. So due to that, you can shift this n carefully, that so that you will be having equivalent form of power series. So it is here n is shifted by n plus 2. So n plus 2 minus 1 is n plus 1, n by n plus 2, an by an plus 2, x to the power n. So this is why we are doing, because we are trying to get every expansion in powers of x to the power n, so that it will be easy to write the coefficient of x to the power n to 0, equate to 0. Okay, so this is why we are doing so. Now, if you multiply it by x square, so I'm originally multiplying here, summation n equals to 2 to infinity n time n minus 1 an time x to the power n. So if you multiply by x square, so x power n, so there is no need to shift anything. So even what you can do is you can start with n equals to 0, because n equals to 0 will give you 0. N equals to 1 will also 1 minus 1 is 0. So that's not a problem. Okay, so that is not a problem. You can write it from n equals to 0. Now, substitute everything in the equation 1 and equate the coefficient of x to the power n to 0. Okay, so what you will get is the following. So y double dash minus x square time y double dash minus 2x y dash plus p time p plus 1 time pi. So this is what the equation. So this is the equation, right? So now substitute everything and compare the coefficient of x to the power n, that we are going to get it as follows. Okay, so this is the coefficient from the 1 minus x square time this one. Okay, this first two term will be the coefficient of 1 minus x square time y double dash. In that you have x to the power n coefficient, and that will be coming from here. So you have this n plus 1 time n plus 2 minus n time n minus 1 time an. So that is going to be coefficient of x to the power n. Now minus 2n an will be coming from here, this term, and the last term, so p time p plus 1 time y, so p time p plus 1 time a will be the coefficient of x to the power n. So that all things will be written here. Now you write down everything. Okay, simplify it. What you will get is the following. So you have this n plus 1 time n plus 2 time an plus 2. Now you take an out and you can simplify this coefficient, that minus n, so minus n time n minus 1 minus 2n plus p time p plus 1. Simplify everything. What you will get is the following. Okay, and you can rewrite then everything in simplified form, and what you will get is an plus 2 is equals to this. Okay, this is will be the final. An plus 2 equals to this. Okay, for n equals to 0, 1, 2, 3, 4 and so on. Okay, right. So what you get is, what you will get, so a2 equals to in form of a0 and a3 equals to in form of a1, right? So see, from n equals to 0, what it will give you, a2 equals to some constant multiple of a0, a3 equals to some constant multiple of a1. Now a4 equals to some constant multiple of a2. Now a2 you can write as constant multiple of a0. So a4 is anyway at the end, it will be coming out as the constant multiple of a0. So what you will, similarly for a5, what you will get is a5 is a constant multiple of a1. So what you will get is even suffixes will come with the constant multiple of a0, and odd suffixes you will get the constant multiple of a1. Okay, so then you write means right, you have you will have the solution in linear combination of a0 time 1 series plus a1 time 1 series. So you will have that series. Okay, so this is going to be, I'm giving you the directly, this will be the form. Okay, a0 time with the, you have this even powers, right? X square, x power 4, x power 6 and so on. With a1 you will have odd powers, x cube, x power 5 and so on. So that will be there. And that you can also show that what will be the possible radius of convergence for this, that okay, it should be between mod x strictly less than 1. Okay, it should not cross -1 nor cross 1, and at x equals to 1 or x equal to -1, you have seen already this is not analytic function. Okay, right. So this is these are known as, this equation is known as Lysender's equation, and its solutions are called Lysender's polynomial. Okay, so that we are not going into it, but whenever you are going to solve some engineering problems, you are definitely encountered with the some Lysender's polynomial and its properties. So we will try to state it when we will study the orthogonal functions. Okay, that is going to be used, or you maybe see this Lysender's polynomial, okay, in case of developing some numerical methods. Okay, so that's your next, you can say, you maybe next semester you are going to learn with it, or maybe later stage when you are dealing with numerical method case. Okay, so this you can treat as a basic foundation of that. Okay, right. So this actually ends the square power series solution to the second order differential equation. Now, what we are going to prove is, we are going to establish the Sturm separation theorem, which guarantees that if you have two linearly independent solution of equation of second order homogeneous linear differential equation, okay, then they will never have the common zero. That means y1 and y2 will not be vanishes at the same point. That's the very first thing. And second point is, if you take two successive zeros of suppose y2, okay, then y1 will vanishes exactly once between them. Okay, means you will have between two any successive zeros of another solution, you will have the 1 0 of the other solution y. So you can look at the simple case like y double dash plus y equals to 0, okay, for which you have two linear independent solutions sin x and cos x. So when you try to plot the graph of this, you can always see that between any two zeros of sine function, you will have exactly 1 0 of cosine function. Okay, so that can be means given as simple example of this problem. Okay, and it's purely based on the proof of the proof will be based on the purely based on the Wronski. Okay, so since y1 and y2 are linearly independent solution, means their Wronski will be non-zero. Okay, will never be zero. Okay, right. So that's we are going to use here for the proof of this equation. Okay, right. So since I already mentioned y1 and y2 are linearly independent, so therefore this the Wronski of y1 and y2 will never be zero. Okay, so further, since this y1 and y2 are solution, means second order differential equation, means they are two time differentiable, means the first derivative and function, they are continuous, so w becomes continuous function. Okay, so w is continuous because product of two continuous function is continuous and sum of two continuous function is continuous. Okay, you can use that fact here. So it will have the constant sign, means it will never change sign. Okay, means if w is positive, it is positive. If either w is positive or w is negative, it may not be possible that at some interval it taking the positive value, at some interval it takes the negative value. Otherwise, there will be a point where the w vanishes, or you can say then Bolzano's property. Okay, that Bolzano's property gives you guarantee that there is a solution. Means that means w vanishes at some point inside between interval, means but which is never be possible because the Wronski will never be zero for this linear independent solution over the interval a to b. So this gives you guarantee that it either W strictly greater than 0 or W strictly less than 0. Constant sign means like it will be fixed. Okay, let us take two successive zeros of y2. Okay, so I already mentioned y1 and y2 cannot have common zeros. So if y1 and y2 have common 0, so let's say x1. Okay, so y1 at x1 is 0, y2 at x1 is 0. So w at x1 is also 0. That is not possible, because otherwise this condition will not be true when they are linearly independent solutions. Okay, so this is not possible. So this part, this thing cannot be possible. Okay, let us assume that x1 and x2 be two successive zeros. Okay, so at x1 and x2, what will be the possible values of this Ross scheme? Because y2 at x1 is 0 and y2 at x2 is 0. So this part will not be there. Only this y1 at x1 into y1 and y1 at x2 into y2 dash at x2 respectively. So this is what is at x1 and x2 value. Now, W has constant sign over the interval x1 to x2. That's very sure. Next, y2 has two successive zeros of y2. So what does that mean? It means that y2 dash x1, okay, will be increasing and y2 dash x2 will be decreasing, or vice versa, means y2 dash at x1 is decreasing or y2 dash at x2 is increasing. That's only the possibility when you have two successive zeros of y2 because of the x prima case. Okay, right. So what it gives you, this gives following that y2 dash at x1 and y2 dash at x2 will have opposite sign. That's now I have told you. Okay, why it is so? Because they are successive zeros of y2. Okay, right. So since w has constant sign, so now what you can have is you can multiply these two, w at x1 into w at x2. So what you will get is y1 into x1, y2 dash at x1, y1 into x2, y2 dash at x2. So since they have the opposite sign, so y1 at x1 into y2 at x2 will also be less than 0. Okay, because so y2 dash at x1 and y2 dash at x2 is less than 0. So this also should have, this product should have also have less than 0. Okay, that's the only possibility. Okay, now since y1 is continuous, then Bolzano's property implies that y1 has a 0. Okay, so Bolzano's property gives you guarantee that if you are able to identify 2 points over which the function is continuous and it has opposite sign, okay, then it has a 0 on that interval x1 to x2. Okay, right. So this gives you the proof that between any two successive zeros of y2, there is at least one zero of y1. Similarly for converse case. So you can similarly, you can start with two successive zeros of y1 and then you can show that there is exactly 1 0 of y2. Okay, right, right. Okay. Now you have this following result, okay, which gives you very important foundation for establishing the Sturm comparison theorem. Okay, right. So you consider the very special case of second order linear homogeneous differential equation. Okay, so this is here by equation 1. So you have y dash is absent here. Okay, so y dash is no more here, and y double dash plus q of x times y equals to 0 with q is a positive function. Okay, so let y be a non-trivial solution of this homogeneous linear second order differential equation where the coefficient of y dash is 0 and coefficient of y is positive function on a closed interval here. So then y has at most finitely many zeros in this interval, means you will be only able to locate finitely many points on the interval where the function becomes or where the function vanishes. Okay, so this has a very simple proof to establish this. Means so you can start with the contradiction that it has, suppose, infinitely many zeros in this interval. What will happen in this case? So if you have infinitely many zeros, means there are x1, x2, there is a sequence of zeros, okay, distinct from a point x0, such that so and so things happen. Okay, right. So what you will have the following. So let y has infinitely many zeros in closed interval AB. Okay, so then what will happen is there exists a point x0 and a sequence xn in AB with the property that xn not equals to x0 for all and xn converges to x0. Okay, and y at xn is 0. So they are the zeros of x, y. Okay, so that is very simple to generate. Okay, so that is very simple to generate, that they are with the property that xn not equals to x0, distinct from x0, and it converges to x0. Okay, that you can, again, you can, if you are not able to know that, you can revise the concept from the sequence cases. Okay, cluster point. Okay, right. So what it will imply now? So y is a non-trivial solution of this, means y and its derivative exists, means y function is continuous. So once function is continuous, means you have xn converges to x0, implies y at xn will also converge to y at x0. Okay, so what it gives you, what is y at x0 is nothing but limit of y at xn, but each y at xn is 0, so y at x0 is 0. Okay, now since it is two-time differentiable, so first derivative also continues. Okay, so this implies y dash at xn is converges to y dash at x0. Okay, or what you can derive is as follows. So you have, this is y dash at x0 is nothing but y dash at xn. So what is that? Y dash at xn is limit of y dash at xn. So y dash at xn is limit of y at xn minus y at x0 divided by xn minus x0. Okay, but since y at xn is 0, y at x0 is 0, xn is not equals to x0. So 0 by xn minus x0 is 0. So for each n, this term is 0. Okay, so limit of 0 sequence is 0. Okay, so what we have observed from here now? So if we started with the assumption that y has infinitely many zeros in AB, then we are able to identify a point, okay, x0, at which y at x0 is 0 and y dash at x0 is also 0. Okay, so then it gives you guarantee that y becomes a trivial solution. Why? Because of the uniqueness of the solution. So you can recall the following statement. Okay, if you recall this following existence and uniqueness theorem, let px, qx, and rx be continuous on a closed interval. If x0 is any point, and if y0 and y1 are any numbers, whatever, then this equation, this y double dash plus px y dash plus q of x y equals to rx has one and only one solution on the entire interval, such that y at x0 is y0 and y dash at x0 is y0. So you have y at x0 is 0, y dash at x0 is 0 in the previous case, and if you have right hand side is 0, okay, because in the right hand side is 0 in the previous case, so y equal to 0 is also a solution. So, but due to the uniqueness, has one and only one solution, so only possibility is here is trivial solution now. Okay, by using that reason. Okay, but this is a contradiction to the fact that it is given that y is a non-trivial solution. So your assumption was wrong. So therefore, when you have y, a non-trivial solution of the corresponding this equation where the coefficient of y is positive, then that solution will have at most finitely many zeros in the interval. So you can take cos x function, sin x function, so you can take y double dash plus y equals to 0. So qx is there is 1. So q of x is greater than 0, 1 is greater than 0. So you can look at any closed interval 0 to pi or minus pi by 2 to pi by 2 or any interval you decide. So you can see sin x and cosine x curve will cut the x-axis only finitely many times, not infinitely many as oscillations you will take. You will see. between any finite length interval. Okay, so this is what this result will make us observation. Okay, right. So now using this result, we have this Sturm comparison theorem here. Okay, so what it gives you is between any two zero of z, there is at least one zero of y. Okay? So that's what the Sturm comparison theorem tells. Means where y and z are satisfying certain special type of second order differential equation. So let y and z be non-trivial solutions of y double dash plus p of x, q of x y equals to 0 and z double dash plus r of x times y equals to 0, where p and q, q and r are positive functions such that q is greater than r. Okay, so you have q and r, both are greater than 0 positive functions. Okay, and q than r, so that is given to us. Okay, so when q is greater than r, so then y vanishes at least once, so maybe more than one time. Okay, so that we are not sure. Okay, so then yx vanishes at least once between any two successive zeros of zx. Okay, so for example, what you can look at is you have this is you have this is a part of your project as well. So you can take one example like you have taken two equations, so y double dash plus 4y equals to 0 and y double dash plus y equals to 0. Okay, you have two equations. You have z double dash plus, you can say here. So you have z double dash plus z equals to 0. So q is equals to 4, r is equals to 1. So 4 is greater than 1. Okay, so this satisfies both the condition of this Sturm comparison theorem. Okay, so that guarantees that. So you have the solution. So y solution, you have sine 2x cos 2x, and here you have the solution sine x cos x. So you take any two zeros of sine x. Between any two zeros, you will have one zero of sine 2x, at least one. Okay, maybe more than one. So you can start with, now instead of 4, you can take 9, sine 3x, sine 4x, and so on. Okay, and you can try to plot the both curve with sine 4x versus sine x, sine 2x versus sine x, and so on. Okay, so you try to plot them and you will immediately have those the flavor of this result. Okay, so right. So again, the proof is beyond the scope of this our course, but I will be happy to give you a like a stepwise some of the proof is very simple here. Okay, so let me give you very simply. So let you start with two successive zeros of z. So because you want to show that y vanishes at least once between any two successive zeros, so let's say x1 and x2 are two successive zeros, means z of x1 is and z of x2 are 0. Okay, and suppose, and that means like two successive zeros means the z will not be vanishing on the open interval x1 to x2. What we need to show that y vanishes at least once on this. So suppose yx is not 0 at all on this open interval. So now, so either it is greater than 0 or less than 0 or okay, right. So it is non-zero on this entire interval, right? Means either it is lies above the x-axis or below the x-axis. There is only two possibility because y is a continuous function. So without loss of generality, we may assume that both y and z are greater than 0. Okay, right. So otherwise we can work out with the problem, work out with the equation. We can replace y by minus y. Okay, and we can still work out with this assumption that without loss of generality, we may assume that y greater than 0 and z greater than 0. We can replace y by minus y in that case. Okay, or z by minus z. Okay, So now what we are going to see is the Wronskian over this open interval x1 to x2. So if you look at the Wronskian of this, so that is y times z dash minus y dash times z. Okay, and you can see that w at x1 and or w at x1 is from here y at x1 times z dash at x1, and w at x2 is equals to y at x2 times z dash at x2. That you can observe straightforward because z at x1 and z at x2 are 0. Now, if you differentiate dw by dx, if you find out dw by dx, that will be y times z double dash, and this you have all these things you will do. Okay, so what you will have is y times z double dash minus y double dash z. These things will get cancelled. So when you substitute z double dash equals to minus rz and y double dash equals to minus qy from the equation, and then if you simplify. Now, since q is greater than r, so q minus r is positive, y is positive, z is positive, so this product is positive function on x1 into x2. So what it implies, so you can integrate over the interval x1 to x2, you can look at the Riemann integrable. Okay, so Riemann integrable, so if f is positive, so then integration of x1 to x2 f of x dx also remain positive. So what it will give you is the following. So left hand side becomes w of x2 minus w of x1 if you integrate the left side, because you are integrating with respect to x. Okay, so that will become w of x2 minus w of x1. This is positive, means w of x2 is greater than w of x1. Okay, right. Now you observe that w of x1 is this and w of x2 is this. Okay, and since again by using the fact that x1 and x2 are the successive zeros of z, so z dash at x1 and z dash x2 will have the opposite sign. So when you multiply w of x1 into w of x2 from 2, what you will observe? W of x1 into w of x2 is greater than w of x1 square, right? So that will give you that w of x2 is always positive, you can say. Okay, now if you multiply w of x1 into w of x2, what we will observe is, okay, then what we will observe is w of x2 into w of x1 is less than equals to 0. Okay, why? Because y at x1 into y at x2, okay, so they means that may be equals to 0 or not equals to 0. So from open interval x1 to x2, y at x1 and y at x2 are positive. Sorry, y is greater than 0 on x1 to x2. So at x1 and x2, it may attain the 0. We don't know. Okay, whether they have the common 0 or not, we don't know. Okay, right. So what we can have is, at least we can have strictly less than 0 or at the most equality sign. Okay, because this is negative, this will be positive. Okay, but this contradicts the above fact. Okay, w of x2 times w of x1 is greater than 0. So your assumption was wrong, and what you have concluded that yx is non-zero on this interval means yx is equals to 0 at least one point on x1, x2. Okay, maybe more than one time. So that's already given. So suppose you can take, so you can work with different value of q equals to 4, q equals to 9, q equals to 16, and so on. Okay, and you can try to identify how many number of zeros are varying. Okay, by just using the online plot graph. Okay, right. Yeah. So next we have the definition of orthogonal functions, and that they are going to play very important role for Sturm-Liouville boundary value problem. So this is why they are important to define. Okay. So orthogonal functions. So we say a sequence of functions fn of x is said to be orthogonal on the following interval. We have already worked over it. Okay. So but now you are going to identify, oh, that sequence is a orthogonal. Okay, so that you already worked over it. So we are going to give some definition to some special type of sequence of functions. Okay, right. So a sequence of functions is said to be orthogonal on the interval, close interval AB if you have the following. So if you have integration of a to b fn of x fm of x dx is equals to 0 if n is not equals to m, and if m equals to n if it is non-zero. Okay, so it means m equals to n means it depends on n, so that's why here the constant is depending on n alpha. Okay, so you can look at the sequence sine of nx. You can look at the sequence cos nx. Okay, and you have to identify carefully the integral, carefully the interval there. Okay, so we are going to look at some examples. Let's say this sequence fn of x equals to sine nx over the interval 0 to pi. So if you try to identify what is the sine nx into sine mx dx, you have to do so. Okay, so what you can do is this, you multiply and divide by 2, 2 sine a cos sine b. Okay, so what it will be is equals to 1 by 2 integration 0 to pi. You have, this is going to be cos of, so you have, this is cos a plus b, so m plus n x minus cos of m minus nx. Cos of, so cos of m plus n is you have with the minus, right? So you have, this is going to be so 2 sine a sine b is cos a minus b, right, minus cos a plus b. Okay, right. Sorry. Okay. Okay, so what you can evaluate from this integral now. So this is going to be what is the value of this integral is 1 by 2 times. So what is the integration of cos? I'm talking about here n is natural number. Okay, so if you integrate cos, it's going to be sine. Now sine of integer multiple of pi, cos sine pi, sine 2 pi, sine 3 pi, sine 4 pi, sine 5 pi, and so on. Sine 0 is 0. Everything will become, so first term will not contribute anything. Similarly, second term will not contribute anything. So this is going to be 0. So whenever m is not equals to n, so this is equals to 0 if m is not equals to n. Okay, so if m is equals to n, what will happen here? Sine square nx, you can use the fact that now means you can use the identity 1 minus cos 2 theta by 2, that 2 sine square theta, and use that fact and you can evaluate that. Okay, so but at least we have seen for m not equals to n, this integral is 0. Okay, for m equals to n, that you can evaluate that what is the possible value, what is that constant value alpha. Okay, right. So let me give you okay, so alpha n is equals to 1 by 2 integration, you have 0 to pi, you have sine square nx dx, so it is not 1 by 2, so you have, this is okay, so this is equals to, you have, this is, you multiply and divide by 2, so you have, this is 1 by 2 time integration 0 to pi 1 minus cos 2 nx dx. Now you can see cos integration is again sine, and sine, sine pi is 0, sine 0 is 0, so everything will be turned off, so pi by 2. Okay, so what you observe, 0 to pi sine of mx times sine of mx dx is equals to 0 if m is not equals to n, and pi by 2 if m is equals to n. Okay, so this gives you that that this sign of adx, this sequence of functions will be orthogonal, okay, over the interval 0 to pi. Okay, right. Now similarly you can also identify the second sequence, which is 1 cos x sin x cos 2x sin 2x cos 3x sin 3x and so on, will be orthogonal on minus pi to pi. Okay, so for the second case, you have integration minus pi to pi. First thing is you have cos mx sin mx dx. Let's say first thing this. Whether m is equals to n or m is not equals to n, this will be always 0 for all m and for all m comma n. Why? Because cos is an even function, sin is an odd function. Okay, definite integral property will give you that is equals to 0. Okay, now minus pi to pi sin mx cos mx, so it's not cos mx, so sin nx dx, and you have another integral is minus pi to pi sin of, or sorry, cos of mx into cos of nx dx. Now, as like we have done previously, multiply and divide by 2 in the both cases. And you can write this as 1 by 2 integration minus pi to pi. You have this is cos of m minus nx minus cos of m plus nx dx. And here you will have the 1 by 2 integration minus pi to pi cos of m minus nx plus cos of m plus nx. Now in the both cases, if m is not equals to n, so cos integral is sine. Okay, so sine multiply integer multiplication of pi or integer multiplication of minus pi. So both term will not contribute 0 if m is not equals to n. And that is also will come out to be 0 if m is not equals to n. So for the m equals to n case, you can discuss separately. Right? So this sequence will also satisfy the orthogonality condition over the interval minus pi to pi. And you will see this sequence will be very useful for defining the Fourier series of the main function. Okay, so that we are going to learn is maybe tomorrow morning lecture. Okay, right. Now what more is here is we can so there is, this is a very particular definition of orthogonality condition. Okay, so now if in case here alpha n is equals to 1, suppose alpha n is equals to 1. So if in case alpha n equals to 1, we say that with everything same, means the sequence is orthogonal, and this for m equals to n, this integral value is 1. We will say it is, instead of orthogonal, we will say it is orthonormal. Okay, so that will be more useful in your upcoming classes, it's like in the next or next semester when you learn about the inner product spaces, okay, orthonormal sequences and all. Okay, that will be more useful there, that definition. Okay, now moreover, so there may be a chance that this type of integral may or may not be possibly 0 for different n or m, means n not equals to n. So there may be a requirement of introducing one more function in this product here, so which we may denote it by w of x, which is called, means you are going to weight, means this product you are going to weight. So means it's kind of a weighted integral now. Okay, so if this weighted integral becomes the 0 for n not equals to m, then we will say it's orthogonal with respect to the following weight function. Okay, so that we are going to, that's going to be general property or general orthogonality condition. Okay, so which is a positive function, w is a positive function. Okay, right. So as already mentioned, if fn, the sequence is orthogonal and this alpha n is equals to 1, then this sequence is called orthonormal sequence of functions. Okay. And a more general type of orthogonal property is defined by, so as already mentioned, that we have introduced a weight function in the product of these two functions. Okay, there may be a chance that fn into fm, okay, that means that integral over it may not be 0, but if you multiply by a weight function, that will satisfy all this property. Then this sequence is said to be orthogonal with respect to the weight function w. And that is very important when you talk about the numerical formulas for when you try to derive the numerical schemes, means like in quadrature rules. Okay, by using Chebyshev polynomial and all other polynomials, where you will learn what are the this form of this weight function, that you will learn there. Okay, right. Okay. Right. So now with this definition of orthogonal functions, we are now in position to solve Sturm-Liouville boundary value problem. Okay. So this is a very general form of Sturm-Liouville boundary value problem. Okay. Okay, but you are going to work with a very specific type of Sturm-Liouville boundary value problem, at least in this course. Okay, so this is a very, I'm giving you a very general form of Sturm-Liouville boundary value problem, but we are going to restrict with some very special type of Sturm-Liouville boundary value problem. Okay, right. So an ODE of the following form. So if you are able to write the ODE of second order differential equations, if you open this first term, so this is going to px times second derivative plus px time, sorry, first derivative into p dash of x. Okay, and arrange all the coefficients and make a standard form. Okay, so you can always able to write it in the following form. So y double dash plus p of x time y dash plus q of x time y equals to 0. That you can always do, okay, by opening up. Okay, or if it is possible to rewrite form into this form, it's like this complete one I'm talking about. Okay, then it will say this is Sturm-Liouville problem, boundary value problem, because you have been given the problem along with the boundary condition. Okay, so here at 2 points A and B, okay, the 2 points x equals to A and x equals to B, you have known the following boundary conditions. So it may be means as already told that, like say suppose the y at 0 is something given to you. Okay, and y at pi is something given to you, means you are investigating over the interval 0 to pi. Maybe y dash at 0 and y at pi will be given, or maybe y at 0 and y dash at pi is given. So, or linear combination of y at 0 and y dash at 0, y at pi and y dash at pi. So there are various form of boundary conditions. So that is a general form here, that if the boundary conditions are given in this specific form, c1 y at a plus c2 y dash at a equals to 0, so at x equals to a, so maybe c1 is 0 or c2 is 0, but both cannot be 0 at the same time. Okay, means either you know y at a value or you know y dash at a value. Okay, means they are 0, that's only here, right? Suppose c1 is 0, so that will give you y dash at a is non-zero. So if c2 is 0, c1 must be non-zero, means y at a is 0. Okay, so similarly for the second condition, so at least not at least, at most one of them only can 0, d1 or d2 only possible 0. Okay, or you can say at least one of the constant d1 or d2 is non-zero, or at least one of the constants c1 and c2 is non-zero. So if you have the ODE of the following form along with the following boundary condition, then we say that this is Sturm-Liouville boundary value. Okay, now this lambda here sitting in the product of Q, okay, sitting in the product of Q is called the eigenvalue. It's called the eigenvalue of this Sturm-Liouville value problem. Okay, and associated solution. So when you are trying to write down the solution, it will certainly depends on lambda, this constant. That associated solution will known as eigenfunctions. Okay, now those eigenfunctions will come out like a sequence of functions, and they are going to be orthogonal with respect to the weight function. And you can see by the theory, it has been already established that weight function is nothing but the Q. Okay, so all these information, so that is why it is important to write the ODE, that's Sturm-Liouville value problem, in the following form. Then it will be easy to find out what will be the eigenvalue possibly, and what will be the weight function for that orthogonal sequence. Okay, so that is why it is important. Now existence and uniqueness is guaranteed once you have P, Q and R are continuous function. Q must be greater than 0 because it's going to be a weight function. Okay, so let's look at some problem and see how we will be able to get all these things. Okay, let's see that. So it's all things are mentioned here where C1, C2, D1, D2 are real constants, and at least one of C1 and C2 is non-zero, and at least one of D1 and D2 is non-zero. Okay, both cannot be zero. It's like C1, C2 both cannot be zero at the same time, and D1, D2 cannot be zero at the same time. Okay, right. So let's consider this first equation, very simple equation. Lambda equals to 1, you know what is sin x, cos x are the form. When you have lambda equals to 4, so you have sin 2x, cos 2x are the solutions, and so on. Okay, so let's see. So when you substitute the initial conditions, but cos 2 pi is 1, so sin 2x will be the solution. Okay, so sin function will form the solution for this case when you have these boundary conditions. Okay, now so let's look at this general equation. So if you if you want to write in that special form, that's nothing but d by dx of 1 time dy by dx plus lambda time q of x plus r of x time by equals to 0. So what is px is 1, what is qx is 1, and rx is 0. Okay, for the Sturm-Liouville boundary value problem. So for comparison, you can get the following: p of x is 1, q of x is 1, and r of x is 0. So this is greater than 0. Okay, so this information we can find out by comparison. Okay, now so there are 3 possibilities: either lambda equals to 0, lambda less than 0, or lambda greater than 0. Okay, so let's take the first case, lambda equals to 0. Okay, right. So in lambda equals to 0, you have y double dash equals to 0. You can 2 time integration, what you will get the line, equation of line. But if you substitute this boundary condition, y at 0 is 0 and y at pi is 0. So what you will get? C1 and C2 both constant will become 0, means only trivial solution possible. So, but we are not interested here in trivial solutions. So this case will be discarded. Okay, right. So now let us consider the next case, means lambda is negative. Okay, so if lambda is negative, means lambda is equals to negative of some k square. Okay, so I can write lambda less than 0 means lambda equals to minus time k square, where k is some r, real number. Okay, and if you recall, what will be the Auxiliary equation is m square minus k square equals to 0, means m equals to plus minus k. Okay, so in that case, the general solution is nothing but c1 times e to the power kx plus c2 times e power minus kx. So I have changed here c1 e to power minus kx plus c2 times e power kx. Either way is okay. Okay, right. So now you can now apply the boundary conditions. So y at 0 is 0. So x equals to 0. So e power 0 is 1. So c1 plus c2 equals to 0. So y at pi equals to 0. Replace x equals to pi. You will have 0. Now solve these two equations in two unknowns. Again, you will get a trivial solution. So this case will also not possible. Okay, or you can say this case will be discarded because we are not interested in trivial solution. Because trivial solution anyway is going to be to solve the Sturm-Liouville value problem. Okay, but we are interested in non-trivial solution. So only third case is, let's say lambda is greater than c. So means lambda equals to k square. For some k belongs to R. Now you can see the y double dash plus k square y equals to 0. So auxiliary equation is m square plus k square equals to 0. M equals to plus minus ki. So its general solution is c1 times cos kx plus c2 times sin kx. Now y at 0 is 0. What is implied? So since sin 0 is 0, so second term will be not coming. c1 times cos 0. Cos 0 is 1. So c1 equals to 0. So that is coming. Now y at pi equals to 0. So c1 is 0. So what is y h now? c2 sin kx. Okay. Now if you replace x equals to pi. Okay. So what will happen? It is c2 times sin k pi. Now see. So see, if c2 is 0, so there are two possibilities. Either c2 is 0 or sin k pi is 0. Okay, right. So now if c2 is 0, then this becomes a trivial solution, but we are not interested in trivial solution. So we should means we are here assuming that c2 is non-zero, and without loss of generality we can assume that c2 is 1. Now, so only possibility is sin k pi equals to 0. So for what value of k, if this will become 0, is all possible plus minus n, positive integer, negative integer. Okay, so k is equals to plus minus n. So we call this, as I already mentioned, lambda k. So lambda is earlier lambda is depending on k square. So now it's for different values of k, you have different lambdas. So these lambda k's, which is k square, means is nothing but n square, the eigenvalues of one, we will call them. And the associated solution are called the corresponding eigenfunctions. So yk of x is sin time kx. So what is k? Is square root of lambda k. Okay, so square root of lambda kx, then this will call the corresponding eigenfunction. And what? So this is nothing. So this you have already shown that this sequence sine of nx, you have already shown sine of nx sequence is orthogonal over the interval 0 to pi with weight function 1. Okay, because we have not used any weight function here, right? See, if we have not used anything here, okay, means here what is q? Q value, q of x is 1 in this case. Okay, so this is with the weight function, this becomes the orthogonal function. So what is q? It is also qx is 1. So with respect to this weight function, it is orthogonal. Right. So let us take another example. So ykx is orthogonal on 0 pi with respect to the weight function qx equals to 1. Let's take another equation, same equation, but with different boundary conditions. Okay, right. So it is different conditions, so you have to look at case again individually. Okay, so lambda equals to 0 case, again you will you can obtain a solution as a linear equation c1x plus c2. Now, if you apply the boundary condition y at pi pi equals to y8 pi. So that will give you C1 pi equals to minus C1 pi. So C1 equals to minus C1. That is only possible. C1 equals to 0. Now y dash at minus pi equals to y dash at pi. So y dash, what is y dash is C1, right? Okay. So what is y dash is C1 only. So what is y here? So y equals to C2. Y dash of minus pi is 0. Y dash of pi is also 0. So both are the second condition is automatically satisfied. Okay. So y equals to C2. So but you can see because of the uniqueness, C2 must be 0. Okay, because the solution y equals to 0 is also the solution which satisfies y8 minus pi is y8 pi. Okay, and y equals to constant. So that enforce you to C2 to be 0. So only trivial solution possible in that case. Uniqueness of the solution. So, but we are not interested in. Okay, right. So now case 2, let lambda is negative. So you have this lambda is a minus k square. You have the general solution of the following form. Now apply the boundary conditions. Again, you observe that C1 equals to C2. Both conditions will give you first condition will give you C1 equals to C2, and second condition will give you C1 equals to minus C2. Okay, so if you solve these two equations, you will get C1 and C2 both are 0. Okay, right. So only trivial solution possible in this. Okay, so now for lambda equals to k square means lambda greater than 0 case. So you have the general solution of this form y equals to C1 cos kx plus C2 sin kx. Now apply the initial conditions, apply the boundary conditions. So y at minus pi equals to y at pi. So you know cos k pi or cos minus k pi. Okay, both are non-zero values, but they are same because cos of minus theta is cos theta. You know sin k pi is 0. Okay, you have sin k pi is 0 and sin minus k pi is also 0 whenever k is, because we are interested in the sequence of eigenfunctions. So we are in particular here, what is k is k belongs to natural number. You can see. Okay, I'm interested in particularly natural number or plus minus. Okay, that may be later on. So y at minus pi is equals to y at pi. So what you observe is C1 cos k pi plus C2 sin k pi is equals to C1 cos k pi minus C2 sin k pi. So then you can observe from here, okay, what you will have here is for first condition, what you have, I think, so this implies what you have is C1 cos k pi plus minus C2 sin k pi is equals to C1 cos k pi plus C2 sin k pi. So what will give you is you have the C1 cos k pi will get cancelled. What you have is 2 times C2 sin k pi equals to 0. Okay. Now what if you go for y dash at what you will get is, so this will imply, what this imply is C2 time or sin k pi is 0. Means this implies k equals to plus minus n. Okay, right. Now if you go with the second condition, that is y dash at minus pi is equals to y dash at pi. So what does this imply? This implies C1. So you have k times C1, so differentiation, right? So you have, this is minus k C1 cos k pi, okay, and plus C2 plus k C2, you have, this is sine, cos derivative is sine, right? Sine k pi plus k C2 cos k pi is equals to, okay, y dash at pi. So what you will have is C1. So what is y dash from here is y dash is k times C1 kx with minus sign plus k times C2 cos kx. So y dash at minus pi. So minus minus plus k C1 plus k C1 sin pi plus k C2 time cos k pi is equals to minus k C1 sin k pi plus k C2 cos k pi. So this will again get cancelled. So what you will have is again sin k pi equals to 0. This implies k equals to plus minus n. So both the conditions will give you the same thing, right? Okay. So this implies lambda equals to n square. Okay. For k equals to 0, 1, 2, 3, 4 and so on. So what you will observe here, so you will observe this for k equals to 1, you have 2, so for k equals to 0, you have cos 0 is 1, sin 0 is 0. Okay, so with normal, so for you can, without loss of generality, you can assume this constant to be C1 equals to 1, C2 equals to 1. There's not a problem. So for k equals to 0, so if I assume, let's say, so k equals to 0. So what is yk is equals to y0, that is 1. For k is equals to 1, okay, what is yk is cos x, okay, and yk is, you have sin x. Cos x plus sin x was there, right? But still, you can take the, consider the case C1 equals to 1, C2 equals to 0, C1 equals to 0, C2 equals to 1. Okay, so for each correspond to each k value, you will have two eigenfunctions, you can say. For k equals to 2, you have yk is equals to cos 2x, one eigenfunction, another function is yk is sin 2x. And you know, 1 cos x, sin x, cos 2x, sin 2x, okay, cos x, sin x, cos 2x, sin 2x, and so on, sin 3x, cos 3x, and so on. Just now we have shown that this is the orthogonal sequence over the interval minus pi to pi. Okay, so we have already seen, and with respect to the weight function is qx is equals to 1 in that case. Okay, so that we have already shown, I think. Yes, in this case here, so we have already shown this here. In all the cases, the weight function wx is 1. So I think we can add here. Okay then. Thank you.